Good afternoon, everyone. If you're listening or just joining, I'm going to start soon. Just indicate by show of hands that if you can hear me. Okay, thank you. Thank you very much. Now, almost 12, let me check. Yes, it's 1 o'clock. Well, at least from my watch, it might be a little bit behind. Let me see. We are doing today magnetic fields, okay? Magnetic fields. Very important concept in electromagnetism. It is one of the three big topics that you'll be doing this entire semester, being the first being electric fields and all that goes with it, the second is magnetic fields, and the last one is optics. I just want to shift here quickly. But before I do that, just some background before I start on magnetic fields. Okay, if someone is recording. Okay, magnetic fields. Okay, I'm going to start now. Just a little bit of a revision on magnetic fields. If a charged particle moves in a uniform magnetic field, so if we have a charged particle in a magnetic field and its initial velocity is perpendicular to that field, the particle will move in a circle, right? And the radius of that circle will be, this is for if a particle moves in a uniform magnetic field and its initial velocity is perpendicular to the field, then its velocity will be in a circle, or rather its motion will be in a circle with radius m, which is the mass of the particle, v multiplied by v, its velocity, over its charge multiplied by the strength of the magnetic field. This is how you get the radius of that circular path of a particle inside a magnetic field. Now, second thing, for a straight current carrying conductor, the force of the magnetic field is equal to the current multiplied by the length of the current, or the length of the conductor carrying the current, crossed with the magnetic field, and that gives you the magnetic force exerted on the conductor. This is the magnetic force exerted on a conductor. And the last thing, the force on a particle inside a magnetic field. The force on a particle inside a magnetic field, the magnetic force B, is equal to the charge of the particle multiplied by its velocity crossed with the magnetic field. These are the most important for magnetic fields, these three formulas that you need to know. Okay. Now on to some questions regarding magnetic fields. The first one, it has to do with the difference between magnetic and electric fields. Okay, I just want to show that there. Okay, everyone can still see, I'm still sharing. Nice. I'm just checking here. Okay, wonderful. Now, One reason why we know that magnetic fields, this is question 1, give one reason why we know that magnetic fields are not the same as electric fields, or rather one reason why we know that magnetic fields are not the same as electric fields is because the force exerted on a charge plus Q. Now let's think about this. What do we know about the force exerted on a charge plus Q? The electric force exerted on a charge plus Q, the electric force is equal to Q, the charge, multiplied by the electric field. This is for an electric field, E field. This is the force due to an electric field on a positive charge Q. Now, what else can we tell about this? Because this Q is positive, because Q here is positive, okay? Because Q is positive, the force vector, this force vector will points in the same direction as the electric field, okay? The electric force points in the same direction as the E field, as the electric field. So the electric force on a positive charge points in the same direction as the electric field vector. So in short terms, or in other words, the electric force is parallel to the electric field. The electric force is parallel to the electric field. What do we know about the magnetic force on a positive charge? This is the positive charge. What do you know about the magnetic force on a positive charge? The magnetic force on the positive charge is equal to the charge, the positive charge, multiplied by its velocity crossed with the magnetic field. In this case, what do we know? This is the velocity, that's the magnetic field. Since this is a cross product, it means that the resulting magnetic force here must be perpendicular to both the velocity and the magnetic field. So, the magnetic force in this case is perpendicular to both the velocity and the magnetic field. In the previous, for the electric force is parallel to the electric field, but in this case the magnetic force is perpendicular to both the magnetic field and its velocity. So let's look at our options that they provided here. The question again is, give us one reason why we know that the magnetic fields are not the same as the electric fields. Because one reason why we know the magnetic fields are not the same as the electric fields is because the force exerted on a charge. So we need, in terms of forces, we need to look at it in terms of forces, and we did that. The electric force on a positive charge, is parallel to the E field, the electric field itself. So the force exerted on a charge Q is parallel to an electric field and perpendicular to the magnetic field. Yes, that is correct. It's in the same direction in the electric and magnetic field. No, that is incorrect. It is parallel to the magnetic field. No, it's perpendicular to the magnetic field. It is zero if the charge is not moving. No, the electric field does not require the charge to move. And is in opposite directions in electric and magnetic fields, that is not correct. So the only viable answer is A. It is parallel to an electric field and perpendicular to the magnetic field. So the answer is A. For magnetic and electric fields, when you compare them, the force for the electric field is in the same direction as the force on a positive charge in an electric field is parallel to the electric field, the direction of the force, and the force in a magnetic field is perpendicular to the magnetic field. And of course the charge must be moving in a magnetic field. Question number 2. A spatially uniform magnetic field cannot exert a magnetic force on a particle in which of the following circumstances. There may be more than one correct statement. So the question is basically asking, in which of these conditions would a spatially uniform magnetic field not exert a magnetic force on a particle? So in which of those conditions would a uniform magnetic field not exert a magnetic force on a particle? Let's look at what a magnetic force is. Magnetic force is calculated in two ways. So you need, just check here, you need the charge. So you have the charge, you need its velocity and the magnetic field. They tell us that the magnetic field is uniform, so we have that, and the particle is there. And then we need the velocity too. We need a charge, the magnetic field, which is already been given. We need a velocity. So which of the following is correct? When will there not be a magnetic force? When the particle is at rest? Yes. A. When the particle is at rest, there will not be a magnetic force. The magnetic field will be 0. When the particle is at rest, there will not be a magnetic field. B. The particle moves perpendicular to the magnetic field, there will be a magnetic force. The particle moves parallel to the magnetic field, there won't be a magnetic force. C. There won't be a magnetic force in C as well. D. The particle is charged, it must be charged. The magnitude of the magnetic field changes with time, there will still be a force even if the magnetic field changes with time. So the only time that there will be a magnetic force is when these two conditions are met. When the particle is at rest, meaning V is 0, so there won't be a force. And when the particle is parallel to the magnetic field, then there will also not be a magnetic force. Question number 3. These are more conceptually based to determine whether you can understand the concepts that you have been taught. Question 3. A proton moving horizontally enters a region where a uniform magnetic field is directed perpendicular to the proton's velocity as shown below. After the proton enters the field, does it? So what happens to this proton? The question is, what happens to the proton when it enters this magnetic field? The magnetic field is going into the screen and the proton is traveling towards the right. So it is perpendicular to the magnetic field. So what will happen to this proton? So let's look at it. Okay, let's first determine in which direction would the magnetic force be. In which direction would the magnetic force be? Magnetic force is equal to Q V cross B. Okay, which direction would the magnetic force be in this case? Okay, we need that there. By the way, this is called the Lorentz force equation. The proton has a positive charge, so we can write positive Q there. Now, assuming that this proton moves horizontally to the right, it's moving in the positive x direction with positive V. It enters the magnetic field. Did someone just switch on their mic there? Okay, so it enters the magnetic field. Let's say the proton moves horizontally in the positive I hat direction, right? This is the proton's movement. I should write it here underneath velocity. So the proton is basically moving in the positive I hat direction, and it enters this magnetic field, which is into the page, and the magnetic field is into the k hat direction. It's into the page along the negative k hat direction. You can choose that as the, normally we choose that as out of the page as k hat, and then upwards as j hat. So this would be k hat, but please note it is into the page, so it's in the negative k hat direction. This is basically the directions. I'm just writing the directions. Now if you use the cross product of the velocity direction and the magnetic field direction should give you the direction of the force, right? So the force would point, if you use the right hand rule, if you use the right hand rule, you'll see and point your direction, or point your fingers in the direction of the moving particle, and then point your fingers in the direction of the particle which is towards the right. Curl your fingers in the direction of the magnetic field. Your thumb should then point in the direction of the force. So negative I crossed with negative k should be in the positive j hat direction. Okay, so the magnetic force would be upwards. The magnetic force would be upwards according to the right hand rule. So it will be in the positive j hat direction, the magnetic force. Now, what else do we know? Or do we want? They ask us here. A proton moving horizontally enters a region where a uniform magnetic field is directed as shown. After the proton enters the field, does it? So we know that the magnetic force would be upwards in the positive j direction. So this particle is going to be pushed upwards. Because the magnetic field force is always perpendicular to the velocity, it will act as a centripetal force. So it will always push this velocity, or this particle upwards. So it won't change the particle's speed, but it will make it move in a circular path, as explained earlier on. So select one or more. It will deflect out of the plane of the paper. No, that is incorrect. It will not deflect out of the paper. It will deflect upward, moving in a semicircular path with constant speed, and exit the field moving to the left. That is correct. B, it will deflect upwards due to the upward force, magnetic force, and it will exit the field on the left because it's going to be turned around, and its speed will not be altered. So B is the correct answer. C, it will deflect downward. No. It will move in a circular orbit with constant speed and become trapped by the field. No, it will eventually move out of the field and continue to move in a horizontal direction with constant velocity. That's also wrong. So B, the correct answer. Now, question number 4. a charged particle is traveling through a uniform magnetic field. Which of the following statements are true of the magnetic field? So we have a charged particle, let's say a proton, and it's traveling through a magnetic field. Let me rather not draw the magnetic field. Let's just, based on the concept, a charged particle, it's moving through a uniform magnetic field. That means all over inside that magnetic field, its strength would be the same. Which of the following statements are true of this magnetic field? This magnetic field exerts a force that is perpendicular to the direction of motion. The answer is correct. Yes, that magnetic field will exert a force that is perpendicular to the direction of motion, because that is due to the Lorentz force law. So A, the magnetic force will be perpendicular to the direction of motion. The direction of motion is just the velocity, the direction of velocity. So the force will be in the direction of perpendicular to the direction of motion. So A is correct. B, it will increase the kinetic energy of the particle. Not necessarily, no. C, it exerts a force on the particle parallel to the field. That is incorrect. The force will be perpendicular to the field. D, it does not change the magnitude of the momentum of the particle. That is correct. It doesn't change the magnitude of the momentum. In other words, it doesn't change the mass or the velocity. The particle still travels at its original velocity. So D is also correct. And E, it exerts a force on the particle along the direction of its motion. No, it's perpendicular to its direction of motion, according to the Lorentz force law and the right hand rule. If you have any questions, just ask me. These are mostly just questions based on your understanding of magnetic fields and the Lorentz force law. Now, what is the direction? There is question number 5. What is the direction of the magnetic field acting on a positively charged particle moving in the situation shown in figure below? Okay, so there we have the particle. If the direction of the magnetic force acting on it as indicated. So we have that the magnetic force is pointing upwards and its velocity is out of the page. We can then use the right hand rule to determine in which direction the magnetic field is. Okay, so if you point your thumb in the direction of the force and your fingers of your right hand and your fingers in the direction in which the velocity is, and curl your fingers at a 90-degree angle, you'll see that the magnetic field would be towards the right along the positive x-axis. If I'm not mistaken, if my right hand rule is correct. So if the force is upward and it's coming out of the page, then it is along if the velocity is out of the page and the force is upward, then it's along the positive axis, along the positive axis, positive x-axis I should say. And what did we use to determine that? It's the right hand rule. And you could try it. Just point. You could try the right hand rule. Point your thumb in the direction, the thumb of your right hand, point it in the direction of the force. Then point your outstretched fingers as if you're about to shake someone's hand. Point that in the direction of the velocity. And in this case, it would be in the direction out of the page. Okay. And if you curl your fingers at a 90-degree angle, that direction would be in the positive x direction, and that would be the direction of your magnetic field. And that is how you use the right hand rule. You could try it as you're sitting there or when you're watching this. Question number 6. These are not calculation based problems. They're all conceptual questions or understanding what is happening. So we have question 6. A magnetic field is directed out of the page. Another one using the right hand rule, I believe. A magnetic field is directed out of the page. Two charged particles enter from the top and take the path shown in the figure. Which statement is correct? So you need to say which statement is correct. The direction of the path depends on the magnitude of the velocity, not on the sign of the charge. That is wrong. Wait, what question is this? Number 6. Okay. So now a positive charge, if you were to use the right hand rule, and if it's positively charged, it will curve towards the left, and if it's negatively charged, it will curve towards the right. How do we know this? It is from the right hand rule for a particle moving downward into this field. So the particle is moving downward, which means its velocity is downward, correct? Now the direction of the force, they tell us there, the magnetic field is directed out of the page. So the direction of the magnetic field would be in the direction of your palms. So you would point your fingers downward, but your palm would point out of the page. And if your palm points out of the page, then your thumb is pointing towards the left, and that is for a positive charge. So for a positive charge, it is scenario 1. Obviously, in the opposite direction, for a negative charge, it is scenario number 2. So let's see which one of these statements is correct. You only have to use the right hand rule. Point your fingers downwards and your palms in the direction of the magnetic field, which is out of the page. And then your thumb would point in the direction of the, first of all, it would point in the direction of the, in which a positive particle would feel a force, and then obviously the opposite would be for a negative particle. Now the questions are, or rather, if the magnetic field is directed out of the page and two charged particles enter from the top and take the paths that are shown in that figure, which statement is correct? I've already told you that, or we've determined that a positive charge would move in the direction of situation 1 and the negative charge would move in the direction of situation 2, if I did my right hand rule correctly. They tell us there that the right direction of the paths depends on the magnitude of the velocity. That is wrong. Particle 1 has a negative charge and particle 2 has a positive charge. That is wrong. Both particles are not negatively charged. D, particle 1 has a positive charge and particle 2 has a negative charge. I'm inclined to select that one. Particle 1 has a positive charge and particle 2 has a negative charge, and they can't be the same charge. It can only be D is the only one that is correct. Question 7. A charged particle moves into a region containing both an electric field and a magnetic field. Which of the statements below is or are true? So which of the following statement is or are true? If this particle is moving into a region that contains both an electric field and a magnetic field. Again, here you need to know the difference between how an electric field would would affect a charge and how a magnetic field would affect the charge. The particle cannot accelerate in the direction of B. That is false. The particle can accelerate in the direction of the B due to the electric field. And a component of the electric field can accelerate in the direction of the magnetic field. That can happen. B, the path of the particle must be a circle. That is not true. That is false. It does not have to be a circle. C, any change in the particle's kinetic energy is caused by the electric field. That is true. A change in the particle's kinetic energy can only be caused by the electric field, because the magnetic field will make it move at constant velocity. And if it's at constant velocity, there would be no change in the kinetic energy. So any change in the kinetic energy would be due to the electric field. So C is true. Only C. Let's pick only C. Only C is true. Question number 8. There is no, in these set of questions, there are no calculation based questions. They are all mostly just understanding. So question 8. A charge is released from rest in an electric and magnetic fields. Both fields point along the x-axis. So the electric field and magnetic field, same direction along the x-axis. Which of the following statements regarding the charge's motion are correct? Remember, the electric field will try to move it, will have a force parallel, while the magnetic field will have a force perpendicular to the magnetic field. So how will the charge travel? Okay, the magnetic force it's released from rest. Okay, and if it's released from rest, okay, they don't say they have it gains any speed, so we assume they release it from rest, so it's just sitting there. That means immediately the magnetic field will now have no force on it, okay, because it is not moving. If it's released from rest, or it starts at rest, the magnetic field will have no effect on it. So magnetic field 0, while the electric field will move it parallel along the positive x-axis, positive x or negative x-axis, depending on the charge of the particle. So the charge will travel along a straight line path. That is true. Number 1 is true. It will travel along a straight line path because there will be no perpendicular component, because the magnetic force is not applicable here. It will have 0 effect. The charge's speed will change as it travels. That is true, because the electric field will cause the speed to change. The charge will travel in a helical path. That is not true. The charge will travel in a helical path of increasing pitch. Not true. The charge will travel in a circle. Not true, because the magnetic field, for all of them, the magnetic field will not have an effect. So only 1 and 2 would be true. 1 and 2 only. Let me select 1 and 2 only. Question number 9. This is all the right hand rule and the Lorentz force law problem so far. Let's say a charge has an initial velocity that is parallel to the y-axis in the same situation. Okay, so it has an initial velocity parallel to the y-axis in E and B, in both the electric and magnetic fields. Both fields point along the x-axis. Okay, so both fields point along the x-axis. Which of the following statements regarding the charge's motion is correct? It's again the same options. What will happen? Now it has an initial velocity that is parallel to the x-axis, parallel to the y-axis, excuse me, So it's perpendicular to the magnetic field. So now the magnetic field will have a force on it. Okay. So the electric field will point it in, let's say, along the positive x-axis, but the magnetic field, it will point it, since the magnetic field is along the positive and the velocity is along the y-axis, it will move in the k-hat direction. Okay, so we'll have the electric force, along the parallel x direction, and we will have magnetic force in the k-hat direction. The magnetic force is in the positive k-hat direction. Along positive k-hat direction. Now along the positive k-hat direction, that is out of the page. That force is out of the page, and we have one force along that parallel axis. So this thing is going to be, it has two forces on it. So what will happen? The electric force will exert a force on it. This is what's going to happen. The electric field the net force on this thing will be equal to the electric field, the force due to the electric field, plus the force due to the magnetic field. Now, this will be the force on this particle. The magnetic force Fb will cause it to move in a circular motion, because it is moving upwards, but the force is out of the page, so it will move in a circular motion. This is due to the electric field, the magnetic field, excuse me. Now the electric field, it is going to cause it to move along the x-axis. And another thing that the electric field is going to do, plus change its speed. Which means it's going to move faster and faster and faster, or slower and slower and slower. Now if you combine these two motions, a circular motion, so it's in a circle, but it's also moving along an axis and also speeding up, that means it's going to be moving in a helical path with increasing pitch. Along a helical path of increasing pitch, so number 4. Only 4. Question number 10. A magnetic field exerts a torque on each of the current carrying single loops of wire shown. Okay, so here we have these loops of wire. I will show it now. A magnetic field exerts a torque on each of them. Okay. The loops lie in the XY plane, each carrying the same magnitude current, and the uniform magnetic field points in the positive X direction. Which of the following ranks the loops by the magnitude of the torque exerted on them by the field from largest to smallest? Okay, so let's calculate. How do we calculate torque due to a magnetic field? Let me just, here's the drawing. Increase it a bit more. Here's the drawing. We need to calculate the torque due to the magnetic field B. Okay, how do we calculate torque due to a magnetic field? The torque is equal to the current, which is the same for everyone, dotted with the cross-sectional area, with the magnetic field and then the sine of theta, okay? Where I is the current, that is the same for all of them. The current is the same for all of them. B is the magnetic field. It's the same for all of them. And theta is the angle between the magnetic field and the area normal vector. Since all these loops lie in the xy plane, the magnetic field is oriented along the x-axis. Because all the loops lie in the xy plane, the magnetic field is along the x-axis. The normal vector points along the z-axis, so out of the page or into the page, making theta 90 degrees for each. So theta is the same for all of them. So basically, the only thing that is different for all three of them is the cross-sectional area. So the one with the highest area will have the most torque. Okay, we can actually calculate it. The area for, let's say, loop A. For loop A. The area for loop A. In this case, the one with the highest torque will have the one with the highest area will have the highest torque. So let's calculate the area for loop A. That is the rectangle. So it is 1 meter by 2. So that is 2 square meters. That is the area of the rectangle. Now for loop B, the area of that circle, it is pi r squared. What is the radius there? It's from 3 to 4, so it's a half. So 0.5 squared. So its area is 0.785 meters squared. And then finally loop C is a triangle, and its area is a half times its base, which is 1 meter, times its height, perpendicular height, which is 3 meters. So it's 1.5 square meters. So the one with the highest torque would be the one with the highest area. So loop A has the highest torque, loop B has the lowest torque, and loop C has a torque in between those two. So if you rank the loops by the magnitude of the torque exerted on them from field from largest to smallest, the largest would be loop A, then it would be loop C, then B. So ACB, ACB. So number 4 is correct. 4 is correct. And that, ladies and gentlemen, is all that we'll be doing today. We just discussed a whole bunch of concepts that you need to know regarding magnetic fields. I'm going to say goodbye for now, and I hope that you've enjoyed this and that you've learned something. Please remember how to use the right hand rule, and please remember that these conceptual questions are important because they test your understanding, and know how I should, or you should at least try to see how I got to each one of my answers. If you have any questions, you can ask them now. I will just stay on for a few minutes. If you have questions, please ask me now.